Hello, everybody, and welcome to this last online session of the GreenRisk4ALPs Mountain Forest Conference. I am Cristian Accastello. I am a forester working at the Consorzio Forestale Alta Val Susa, but previously PhD at DISAFA, one of the project partners of GreenRisk4ALPs. Here with me to co-chair this session, we have Dr. Stefan Steger from EURAC Bolzano. Hi, Stefan.
Hi.
And the title of this session is Friends of GreenRisk4ALPs, Mountain Protective Forest as Eco-DRR. In this session, we will have 5 presenters that are external from the GreenRisk4ALPs project, but they are topic of and recognizing the role of forest as ecosystem-based solution for disaster risk reduction. We will also listen to this presentation, but if you want to know more about their work, you will also find a lot more information in one of the 2 handbook that the GreenRisk4ALPs project is gonna publish very soon. So I suggest you to keep in touch on our website for the publication of the handbooks. And I also remind you, if you are not still very confident with this platform, that you can interact with both with us, with the presenters, and with the other participants of the conference by the live Q&A that you can find here on your screen or on the meeting hub, which is outside of this this session. Now I leave the floor to Stefan to introduce our first guest. Thank you.
Thank you very much, Christian. So let me introduce our first speaker, Dr. Emanuele Lingua. So he is an associate professor at the University of Padua, Italy, at the Department of Land, Environment, Agriculture and Forestry. And in his research, he mainly deals with stand dynamics, mountain forest management, with a particular focus on forest disturbances. From a methodical perspective, he's using multiple methods from remote sensing, as we will probably see in the next or in this talk, spatial analysis, methods of dendroecology, and so on. So I'm happy that you are here, Emanuele, and yeah, the floor is yours.
I'm glad to be here and to share our activities to the member of the consortium of GreenRisk4ALPs. Today, in this short talk, we just talk on, and I will present 2 case studies that we developed in Rock-the-Alps project that are dealing with the natural disturbances and protection forest, using some new technologies that are available out there. Of course, we are here because we know the importance of protection forest, and in the alpine region, we know that forests are directly protecting inhabitants, roads, infrastructure, human assets in general. And actually, based on the results from the Rock-the-Alps project, we know that almost 20,000 square kilometers of forest Alps directly protect this object. So they are important for the alpine communities. But they are providing this kind of protection, these ecosystem services, in an effective way only if they fulfill some requirements, so they show some particular characteristics. And this is not stable. This is a dynamic ecosystem that is changing, and so these characteristics are changing in time. Sometimes smoothly, sometimes abruptly. And when we are dealing with a forest ecosystem, we cannot forget the natural disturbances. Natural disturbances have a very important role in forest dynamics, but sometimes for our purpose, there's something that is really disrupting our structure, that is helping in preventing some natural hazards. And for instance, since in order to fulfill the protective effect, the protection forest needs to have a particular structure, and since natural disturbances, by definition, are discrete events that alter forest structure, they are really affecting the provision of these important ecosystem services in the Alps. And nowadays we are facing climate change, global change, and we already have seen that we have an increase in frequency of natural disturbances and also in the magnitude of the episodes that are happening nowadays on the forest in the alpine region. After a natural disturbance, what we need to know, we need to assess the damage provided to the forest. So we need to assess the disturbance severity in order to understand eventually the reduction in forest cover or the modification of the stand, mainly the stand structure modification. And we need, after that, so aftermath, to define the residual protective effect of the slope. That is a guarantee by the stand affected by the natural disturbance. We need to define this residual protective effect, and we have to analyze and to assess the role of the biological legacies, all the material that is still there from the biological origin, so like standing dead trees, lying logs, or surviving trees, etc. They still can play a protective effect, but we need to assess and to define this. And after that, we need to know the priorities in the intervention. We have to recover the protective effect. We have to recover the protection function of our mountain forests. In order to do that in a very effective way, we can adopt different methods, but we can use particular tools. There are actually remote sensing tools that are able to characterize a large area with a very high accuracy in a short period. Now we can choose with among different sensors that are available, from laser scanning or radar, so active sensors that are emitting a signal and they are restituting some 3D information about the point on the Earth's surface, or passive sensor like orthophotos, satellite images, like hyperspectral or multispectral information that are very useful in order to derive the health of the vegetation, such as the forest cover. We can combine those information, so the 3D information with the healthy status or the visible information that we can obtain from a passive sensor with data fusion. So we can implement the information we can derive from these sensors. But also we can change platforms. So nowadays, the remote sensing data are no more only derived from a satellite or from airplane. So everybody knows drones, UAV, RPS, etc., but also mobile laser scanning, mobile tools that can survey forest stand when we need. And this is very important. Combining all these two characteristics of the different sensor and different platform, we can almost reach an infinite combination, and so very useful in order to infer and to obtain accurate and very quickly some data on our forest. And this is very important after natural disturbances, because we have maybe a bunch of data before the disturbance, and we need right after the disturbance information of the residual status or residual stands. And in the next slide, I will present two case studies. One is concerning forest fires happening in Italian Western Alps in fall 2017, and the other is the most famous windstorm in Italy in 2018, so the storm Vaia, that affected the Italian Eastern Alps. We move from west to east in this presentation. So the forest fires, fall 2017, we had 9 big fires that affected the mountain forest in the Western Alps, from the Cuneo province to the Turin one, so close to the French border. Big fires. So the range was from 165 to almost 4,000 hectares. That for the alpine region is a quite big area. A total amount of approximately 10,000 hectares have been burned. Among them, more than 7,000 were forest. Then that fall 2017 was the warmest and driest of the last 70 years almost. So really the driest October in the last 60 years and the warmest October since 1958. No precipitation more than 10 millimeters for 50 days and a lot of third episodes. So strong, warm and dry wind that just prepare the forest to be a perfect fuse for that period. The problem was that the majority of the stands were in the slope and were protection forest. So we need to estimate the residual ecosystem service, the residual effectiveness of the ecosystem service provided by that kind of forest. So firstly was the first assessment with Sentinel-2 images that are freely available for everyone. So we extracted the information before and after the disturbance, after the fires, in order to obtain the normalized burn ratio index, the delta one, in order to infer the burn severity, the first burn severity map. Based on the first assessment of burn severity, we conducted a field campaign on a plot on the field where we measured and recorded the composite burn index. That is an index that is referring to the fire severity, and it is linked with remote sensing data. Combining this information with random forest approach and machine learning, we define the fire severity maps, calibrated with the field survey in order to define the high severity, the moderate severity, and the low severity area. Why was so important this? Because after that, combining this information with the forest preeminent functions, and in this particular case, the protection against rockfall, we identify the priority areas of intervention where to devote the effort in order to recover quickly the forest cover, and also the area affected by high severity were in the priority list for the rural development plan of the Piedmont region. Similar approach was for the storm Vaia in October 2018. You know that more than 40,000 hectares have been affected, more than 12 million of cubic meters were lying in the ground. And this was just a first estimate, and is increasing year after years. One of the sites that we selected for the Alps, where we in 2018 measured the forest stand parameter, we accomplished a UAV campaign in order to derive 3D models, was affected by the Vaia storm. And so after the storm, we derived other information, other data, LiDAR in 2019 with orthophotos and field data in order to calibrate. Using this data, we were able to make a perfect change detection concerning the forest cover. Here you see the difference in a Canopy 8 model from the two different LiDAR acquisition. But also, and very important, was also to define the quantity of material on the ground and the roughness value of this material. So deriving the information from the LiDAR data, 20 points per square meter, the LiDAR data coming from the flight in July 2019, we extract with a specific algorithm the roughness value for this slope. And we use this value with the forest cover, residual forest cover, in the Rocky4 3D model in order to derive and to assess the protective effect of the stand. And surprisingly, as you can see from this picture, comparing the before and the after storm output of the simulation, we obtain that the protective effect actually was higher after the storm rather than before the storm. And you see we use Barry-Miriam ORPI indices developed by Dupier in 2016 in order to infer the effectiveness of the forest. And as you can see, all the indexes were higher after the events compared to the previous situation. And so based on this, no savage logging intervention have been accomplished in rock, also in avalanche site, but this is another story. And this is quite important. The important thing is also to monitor the roughness values, so the decreasing in the height of the material and also the decay of the material. And the height of the material can be monitored easily with a UAV acquisition in the following years. So in this very short and fast presentation, we have seen some sensors and platforms and data that can be used in order to assess the protection forest status. They are available. A lot of time they are free, available for everyone. Nowadays, we can also have a very data that are cheaper than the past because we can acquire with using drones and the price is very low compared to 10 or 20 years ago. But there is still a lack of knowledge in forest practitioner and manager. There is a sort of generation gap still, but we are filling this gap year after year. And something that I want to highlight is actually there are not really new technologies, but the application in the forestry sector is still relatively low. So we have to work in this direction to include this up-to-date data in our forest management planning system. Thanks for the attention, and ciao, Charlie.
Thank you very much, Emanuele, for demonstrating us the quite huge potential of remote sensing in forestry. We are running already late, but I would have one question, since there are many practitioners also in this session and part of GreenRisk4ALPs. So from your perspective, so you demonstrated how we can use remote sensing data in combination with machine learning techniques and such it sounds like advanced scientific tools you are using, but in terms of user friendliness, how far are we to efficiently use remote sensing tools also in the sector of forestry?
Yeah, I have to say that recently we made a lot of big steps because we started also to develop like a free tool, also using like Fusion or QGIS, so to implement user-friendly application or procedure in this kind of softwares that almost everybody now knows or can use. So no more like a command line or like in R or very maybe difficult tools for a practitioner, but we are implementing this in open source GIS software. This is really something that will help a lot in the next years. Also here in my department, we are implementing this kind of tools regularly, and it's something that I think in the future will be used by the majority of the forest practitioners all over the Alps.
Okay, thank you very much. I think we are already late, but I want to remind the audience that we have a question and answer section, and the questions, I see that some questions popped up and they will remain there for 30 days. So, and I asked the speakers also to contact the persons and to answer them afterwards. So your questions will not be lost. And with this, I forward the word to Cristian to introduce the next speaker.
Yes, the second speaker of this session will bring us to investigate a slightly different topic, because we will now focus on flood protection by alpine forests. And therefore, I'm glad to introduce Dr. Gerhard Markart, who is head of unit in torrential processes and hydrology at the BFW, the Federal Research Centre for Forest, Natural Hazard and Landscape in Austria. So now we can go on. We can start with the presentation.
Good afternoon. Thank you for the introduction. My name is Gerhard Markart, and my presentation deals with flood protection by forests in alpine watersheds. The lessons we learned from our case studies here in Austria. My thanks go to Michaela Deich, Christian Scheidel and Bernhard Kohl, who assisted me in preparing this presentation. What are the main effects of forests on mountain hydrology? Rainfall interception is higher in forest than in open land. It can amount to several hundred millimeters per year. In addition, the kinetic energy of precipitation is reduced. Normally, forest soils show higher infiltration rates and also higher free storage capacity due to the high transpiration rates of the trees. This, on the one hand, results in less surface runoff to receiving water courses, but can on the other hand produce higher contributions to near surface and subsurface runoff due to the higher macroporosity of the forest soils. An overload situation can occur in case of extreme persistent rain events. In such cases, the runoff hydrograph of the forest sites can approach to that of open land. This can occur on shallow soils with reduced soil water storage capacity, like here on this side, on very cohesive dense soils, or when overland flow from overlying open land occurs in forests. What are the effects of protected forests on runoff at different scales? We analyzed a small testbed in the Silver Valley where 50 years of ameliorative measures have been set, comprising reforestation, afforestation of former pastures, optimization of existing forests and so on. This resulted in a reduction of the former peak runoff value of about 32 cubic meters per second to about 14 cubic meters per second. The possibility of the modeling results have been falsified on traces of runoff events of lower annuality. We did numerous rain simulation experiments and analysis of other data. We did this analysis also on the barren catchment, which had about 46 square kilometers and got nearly the same results. Thus, we dare say that forests play an important role in flood protection also at the mesoscale. What about the effect of forests at the macroscale? Many studies indicate that there is no influence of geology, land cover, and therefore also forests, land use on runoff in persistent rainfall in large catchments. Our analysis of the long-term rain events in the Bregenzer area didn't show any traces of surface runoff in the forests. Well, we got some runoff reactions from karst systems, open fissures in rock, and saw numerous traces of surface runoff and landslides in open land. So also in large catchments, the protective effect of forests at the local level is given. Forests can make a significant contribution to slope stabilization by the spreading of the root systems. They are armoring the upper soil. But on the other hand, they can cause driftwood problem and therefore pose a danger, for example, by clogging of infrastructure. We analyzed the Seigersbach event, which occurred in June 2015 in the Southern Valley. About 200,000 cubic meters of material have been eroded, and you see that more landslides occurred when the slope stabilizing effect of the forest is missing. Here, some years before driftwood management had taken place, it would be more ideal to install a sort of permanent forests with interventions in shorter intervals at such sites. Landslide intensity in forests is not only an effect of substratum and other side factors, it's closely related to type and the intensity of management, that means to forest structure. We observed landslide in forests mainly on open stands in areas which were extensified, that means with uncontrolled succession to forests in parts with high supply of water from upslope and in the transition zone to open land. Concerning the role of protection forests in integrated risk management, that it's difficult to quantify the effectiveness of forests. This is also due to the fact that traditional approaches of flood risk management are static. They should be changed because population is still growing. This causes high area consumption, increased soil seeding and large-scale land use, as can be seen from this picture here. This is an effect which takes place in all altitudes. In addition, we have to face the effects of climate change, the increase of extreme events, drought periods and disturbances. Disturbances like wind throws, snowbreak, browsing of ungulate game animals, and grazing livestock counteract forest protective functions in many alpine countries. We analyzed the change in overall canopy within 15 years in test beds in Western Austria and in the South Tyrol. The black dots mean closed or sparse forests have remained, blue gaps that have remained, red new clearings that have developed within these 15 years, and green where areas have closed. And if you add the numbers of the blue dots and the red dots, then you see that there are many more than the green ones. So we have to face delayed reforestation in many parts of the Western Austria. We are successively losing important tree species for adaptation to climate change, like Abies alba. The forests get destabilized and the protective effect is reduced. Therefore, traditional forest-related approaches of flood risk management need a change. One solution could be ecosystem-based disaster risk reduction by a sustainable management, conservation and restoration of mountain forest ecosystems. This can be achieved by increase of resistance and resilience of the forest vegetation against natural disturbances, by prevention of wind throws, snowbreaker and so on, like shown in these pictures. To reach this goal, several steps are necessary. First of all, there is the development of practical guidelines which can be easily understood and applied by practitioners in the field. We try to do such one concerning optimizing the hydrological effects of protection forests, which can be downloaded on the BFA homepage. Second step should be that legislation and bylaws lead adaptation at all levels and allowing easier implementation and application of guidelines in practice. In addition, the final support for applied research on forest and water must be increased. In addition, the participative processes in flood risk and integrated watershed management must be improved. This could be done by efficient coordination and linkage of all involved bodies like avalanche and storm control service, forest service, all the landowners and all the representatives of the planning institutions in the planning process. Consequently, the Protective Forest Action Program has been released in May 2019. It comprises 35 specific activities to improve the current situation of forests and to ensure their sustainability for our future. Concrete implementation of projects is funded over the Forest Fund, which has not been launched in 2021 in February, and in this frame about 350 million euros shall be spent within the next 4 years for improving the situation of forests in Austria. So thank you, that's it, goodbye.
We have a couple minutes for the discussion. We have a question from the public, and someone from the public was asking if you have any plan to upgrade Zemocost also for broadleaf tree species.
So Zemocost is a catchment model which calculates runoff values for the catchment. So you always have some mean values over a certain type of catchment or sub-catchments. Integration in Zemocost is possible by attributing the correct runoff values. So, for example, for North Tyrol, Bernacoli is just doing a runoff coefficient map, which represents the actual runoff conditions also for forest stands all over Northern Tyrol.
Okay, thank you. Stefan, we can go on with the next speaker.
Okay, but I would have a last question to Gerhard.
Oh, for sure.
Actually, as far as I understood, you observed less a lower landslide intensity in forests compared to other land cover units. Isn't that the case? So how? And of course, this is often observed, but can it also be, or what's your opinion on that? That one may simply underestimate landslides or landsliding under the forest canopy, as in fieldwork or based on remote sensing data, you might not see the geomorphological features actually to map them.
Certainly might be. It was our impression from these 5 communities or 9 communities we did in the Bregenzer Wald areas on more cohesive soils, and there we found that what Massimiliano Schwarz said, that the spreading of the roots in denser tree stands is preventing landslides, especially shallow landslides. We found this proved, and mainly we observed landslides on these 4 types of surface cover I have shown before. It was when landslides in forests occurred, and mainly with interaction from runoff from overlying regions, for example.
Okay. Thank you very much.
Thank you.
So let's move to the next speaker, which is Dr. Christian Scheidel. I will introduce Christian Scheidel. He's a senior scientist at the University of Natural Resources and Life Sciences. So probably most of you know this university under the expression BOKU in Vienna, Austria. And he works at the Institute of Mountain Risk Engineering. Christian teaches geomorphology and natural hazards and does research on alpine natural hazards with a particular focus on debris flow processes. So in this context, he concentrates on the protective role of alpine forests on natural hazards and slope stability. And in this talk, he will give us some insights into the effects of forest cover on torrential hazards, a quantitative approach.
Hello everybody, my name is Christian Scheidel and I'm a senior scientist at the Institute of Mountain Risk Engineering of the University of Natural Resources and Life Sciences, Vienna. Why is forest cover a matter of importance? Let's start by exploring the domain of interest. Forest cover helps to reduce the risk from natural hazards on a large area over long time periods. So forests provide what are called regulatory services, but at the same time forests also perform a variety of other essential ecosystem services. To bring it back to mind, those are provisioning, supporting, and cultural services. However, what we focus on today are torrential hazards and the question, what's the influence of forest cover? This means we are literally in steep catchment areas where torrents can be classified roughly by its catchment area, in this plot given as a natural logarithm at the axis, and its relief energy, here characterized by the average channel gradient indicated at the ordinate of the graph. It can be shown that with a catchment area of about 25 square kilometer, a criterion for typical torrential catchments can be given. Catchment in which torrential hazards such as floods with constantly or temporarily flowing watercourses and most importantly strongly changing discharge occur. But also events are observed which show a strong bedload transport which can lead to damages directly due to sedimentation but also indirectly due to displacement processes. Furthermore, in torrential catchments we are confronted also with events whose sediment transport capacity causes the amount of moving material to equal or even exceed the proportion of flowing water, with its climax denoting so-called debris flow processes which are observed exclusively in torrential catchment areas. So what about the effect of forest cover? Since the 19th century, European countries in alpine regions are historically leader in managing protective forests. Those ecosystems and management techniques can be seen as part of European natural and technical heritage. However, inventory data of Austria show that only half of such classified protective forests have a stable structure. The reasons are often identified as significant aging, a lack of 3 species diversity, or a lack of regeneration areas in need of rejuvenation, causes which, in addition to excessive game pressure, are also due to climate change. In order to find out whether the loss of forest cover can actually already be proven, we conducted the following study. We combined time series of annual forest cover for the last 30 years with information on observed torrential events in more than 10,000 catchments in Austria. Based on 4 predictor groups, general characteristics of the catchment, geomorphometric numbers within the catchment, forest and disturbance characteristics, for which we believe an effect on the occurrence and frequency of torrential events can be shown, we found the following results. Consider the influence of the forest. We can observe that forest cover and patch density have the strongest negative effect on the occurrence and frequency of torrential hazards. Thus, in addition to forest cover, it seems to matter how the forest area is distributed in the watershed. The figure on the lower right shows the same forest area distributed differently, with a more favorable picture in the right in terms of occurrence and frequency of torrential processes. It also gets interesting when we look at the effect of disturbances. Large-scale disturbances have a positive effect on the occurrence of debris flows but show no effect on the occurrence of flooding. For the type of disturbance, we distinguish between disturbances that happening in a short period of time, we call them pulse disturbance, and disturbances being distributed regularly over the study period, so-called press disturbances. Our results indicate that press disturbances can rather be regarded as drivers for torrential processes, whereas sparse disturbances have a negative effect. Having studied the influence of forest cover in general, we wondered, what about the process level? For the initiation of torrential processes and thus indirectly affected by forest cover, a critical amount of precipitation, as well as the sediment availability in the catchment area, are of major importance. Specifically, we ask ourselves whether climate-induced disturbances, reflecting the change in forest cover, influence the rainfall runoff regime and erosion behavior. The latter might act as a predictor of sediment availability. We thus initiated a project called Protected to study the influence of canopy disturbances and runoff and landslide disposition after heavy rainfall events. It was funded by the Austrian Climate Fund. Here we focused on 2 steep and rather small headwater catchments with high relief energies in the Tyrolean Alps, namely the Innerer Lehnertalbach and the Äußerer Lehnertalbach in the Stubaital Valley. This kind of study was based on 200 years of simulation time and referred to 4 climate change scenarios and 1 historical climate projection. We simulated 42 different landscape scenarios with island as land cover input for hydrological simulation by means of CEMOCOST and GeoDOP. Overall, we conducted 2,520 simulations for each catchment and compared the results after 50, 100, 150 and 200 years simulation time. The climate change projections can be characterized by a moderate, a warm and wet, as well as a warm and dry scenario. Coming to the results. Shown are the results for the climate scenario based on historical data. The warm and wet climate scenario and the warm and dry climate scenario. The warm and wet climate scenario is denoted with EBSL 85 and the warm and dry with MOHC 85. In the upper panel of each climate scenario plot, we indicate the deviation of simulated peak discharge from simulated peak discharge based on land cover output without considering disturbance. So you see here the relation of the peak discharge with and without disturbance. And we also stratified the results by management and no-management activities. In the lower panel of each climate plot, you see the magnitude of distributed area relative to the total forest cover per year. Well, the discharge results shown are based on the pooled results of both applied hydrological models, CEMOCOST and GeoDOP, and no significant influence of natural disturbances on the runoff behavior in torrential catchment areas could be detected. Further, there was also no significant change in soil water content for any of the future climate scenarios and disturbance-induced simulated landscapes. However, positive trends describing an increase in runoff due to an increase in the disturbed forest area cannot be completely ruled out visually. Regarding the effect of forest cover on soil stability, I refer to our article in Science of the Total Environment. Briefly, we were able to show that the availability of shallow landslides in steep forested torrential catchments seems to be increased by disturbances in general, but it might be decreased by the occurrence of disturbances for a warm and dry climate reaction, here denoted with MOSC 85. Here, canopy disturbances seem to accelerate the adaptation of tree species to future climate conditions, which is likely to be accompanied by a change in root systems away from flat roots that currently predominate in torrential catchments. So to the outlooking, there seems to be a critical size of disturbance area whose mainly temporal impact is unclear. What makes us ask how much forest cover must disappear in controlled watershed to leave hydrological quantifiable traces. Combining disturbance dynamics with soil moisture dynamics, which means considering also the antecedent rainfall together with a comprehensive hydrological parameterization of the soil, would appear to be useful for the future. However, we do not need to reinvent forest hydrology, but alpine regions and thus most torrential catchments are fast responding domains in terms of system changes, be it climate change, change of exposure, intensive recreational use, or increased use of primary resources. Such systems changes can have long-lasting impacts on the ecosystem services. I believe there is a need for a new scientifically guided discourse behind the aspect of safety approach. If we consider other than regulating, especially protecting ecosystem services in alpine catchments to be increasingly important, future recommendations of targeted interventions or measures as well as adaptation strategies to changes must be based on well-founded, in this case quantifiable scientific knowledge that offers comprehensive but also sustainable answers. Many thanks for the invitation.
Thank you very much, Christian, for this very nice presentation. Yeah, I would have a first question to you. You mentioned that you stratified the results according to management and no management activities in order to elaborate the impact of climate change, let's say it like this. So in your experience, we also in GreenRisk4ALPs tried just to include climate change to elaborate changes in the forest structure, so not on slope stability. But in our case, it became quite clear that the sensitivity of the models to management scenarios is much bigger than the influence of the climate scenarios. So in your case, what's your so when you compare your results according human or management scenario and no management scenario against climate change, what would you think is, or is it the combination which is important, or probably you can elaborate a bit on that?
Yeah, okay, thank you, Stefan. Sorry, thank you very much. The main landscape simulations been conducted with island. The management procedures are based on recent knowledge. So we simulated 100 years in future and stayed on a constant management information on this. There is actually a lot of discussion about these management influences on the landscape simulations, but I have to get off here because we are more from the process point of view. So we just looked at what looks the forest as and what's then the impact on our rainfall runoff simulations. There are a lot of papers in the meantime from Rupert's group from now in TU Munich. They really looking after this, and there is an open discussion about management, yes or no. It's not so trivial because our disturbances, they are stochastically driven, and they are not really connected as far as I knew. So if there is a stochastically we put one disturbance in our simulation and we did a lot of replicates, then that doesn't mean that automatically we have a management. So we had just a constant management as you would have. So there's a weak point in this landscape simulation, maybe in this way.
Okay.
So I'm sorry.
I expected that's not that easy at all.
Yeah.
Other questions from the audience? I don't see any other question So probably I would have an additional one to you.
Yeah.
You worked or you presented work which deals with different spatial scales. So in the last one, it's more local, and in the first one, it's rather a big one. But when it's just from my experience, when you provide decision makers with results or with a map, especially, the scale suddenly doesn't seem to be in some of their minds anymore. So how to explain the explanatory power of the results when you work on national scale or regional scale analysis? As from my experience, people tend to look at their single slope and they point to this single pixel, and then it's quite difficult from my viewpoint.
The first part of my presentation, I think most of the audience, they would say, what's the new aspect on it? Because most of this is experienced, they know it. I mean, that something kind of clear. It's like a baseline shift syndrome happening at the moment. I think so. The elder colleagues, they have learned it, they have seen it, they have all the pictures in mind. We were just like putting different databases or different informations now against, and have been very happy to see what we all expect on a quantifiable version. So the first part gives you just the information or just confirms quantitatively what we all know, you could say. But it's very, very important for me because also knowledge will change in future, and also we need to quantify these things, what I said in the last slide. For the second part, that's not very easy because that's a trick what you're doing in forestry, that you can't wait 100 years to see your results from your experiments. So more and more the people go to simulations. Yeah, I mean, that's there needs to be very concise communication. Maybe I mean, I grew up with this protection communications part, but I feel also rainfall runoff. Last week I was in Switzerland. They said me decades ago the federal Swiss government wanted to know what's really the impact of forest on rainfall runoff. They had a lot of papers and there was not a lot of things coming out. Also, Theo Wien, Göschel did a lot of these things. But if we see our exposure growing, if we see that we bathe much more things, if we see that we bring these events more to the people than by rainfall, than by anthropogenic influences, then I think we need to quantify it a little bit better to avoid just colorful pictures at the end.
Yeah.
Hopefully. That's the motivation behind all this.
Yeah, but thank you very much. So let's move to the next speaker. Christian?
Yes. Actually, your last question, Stefan, was the perfect introduction also for the next speaker, because here we will talk about interactive maps applied to avalanche protection forest. And to do so, we have here with us Dr. Peter Baby with a live presentation. He is the team leader in mountain ecosystem and community ecology at the WSL, the Swiss Federal Institute for Forest, Snow and Landscape Research. So I leave you the floor to Peter Baby with his presentation. Thank you and welcome, Peter.
Thank you very much. I would like to focus on avalanche protection forest and say something from process knowledge to large-scale interaction maps. So we have a lot of knowledge about avalanche forest interactions. For example, in our Institute for Snow and Avalanche Research, we are studying this since the avalanche winter 1951, actually quite seriously. We have a lot of data on avalanches in forested terrain. And actually in the last 20 years, we made quite progress about the quantification of avalanche models in forested terrain. For example, Michael Teich, who is co-organizing or is organizing this conference, did very significant contribution to that. In the last years, we made improvements mainly also in integrating remote sensing data, high resolution remote sensing data, and also in integrating uncertainties in these models. The question from my presentation was quite an applied one. We wanted to delineate avalanche protection forest for large-scale hazard mapping. So we did that. I will show how we did that for the Canton Graubünden. So this is a 7,000 square kilometer area where we live, and the people or the responsible people for the natural hazard in Canton Graubünden wanted us to do large-scale hazard mapping for avalanches. And first of all, we needed to have a good protection forest map, avalanche protection forest map. The criteria for this should be that it should be based on the best possible data, best possible vegetation height models and other digital data. It should be based on good observational data and, wherever possible, on existing guidelines. And it should be comprehensible, fully automatized for the whole region, and verified in the field and with cadastral data. So this was quite a challenge. We did that during the last 2 years and struggled quite a lot with it. But I think the result now is quite promising and good. Yeah. So the basis was topographical and forest structural data of 150 avalanches in forested terrain, one of the bases. And from this, we deduced critical threshold for gap sizes, steepness, tree height, ground cover, and so on. So there were statistics done on these parameters many years ago already. But we took actually also this data that used a logistic model, mainly based on ground cover, gap width, slope angle. And then we used the high-resolution digital terrain model and high-resolution vegetation height models to deduce critical thresholds for forest cover. So when is a forest an avalanche protection forest, and for gap. So when is a gap? So because these two parameters were important for the logistic model. We used the digital terrain model also to deduce surface roughness, which was how we found quite an important parameter in order to improve this avalanche protection model. And we also used a shrub forest layer, which also helped us to improve this model. So from this, we deduced the protection forest index for the whole region. And after verification with cadastral data, with regional experts, with fine tunings, back and forth procedure with the practitioners, we could then finally deduce a map with avalanche protection forest, yes, no, 4 different scenarios. So for rare events, for extreme events, and for frequent events, which are about 10 to 30 years event. So the first models looked like this. These were the preliminary protection forest models for the region now in Davos, where I live and work. And actually, they looked quite promising in the beginning, but when we had a closer look, and also when we let the RAMS models down, when we made the simulations with this avalanche protection forest, then we had too many avalanches actually. So in some parts of the region, the avalanches runouts were all over the place, and we had to make it a bit. We had to improve it a bit. So we had to adjust the models, the first models. One of the improvements was that we integrated terra roughness based on the digital terra model. So this was a map of just a binary variable terra roughness for the region. We also made other improvements and finally had an updated model for the whole region. We see the preliminary model in yellow and the updated model in red. So this was a bit more offensive, and it was an improvement. So we had a very good. It was very good in line with the cadastral data and also with our knowledge from the region. So this is this updated model for the whole region of Graubünden, for the whole canton, and in the small figure you see how it very nicely fits actually to the forest structure. So open forest, this was not avalanche protection forest, or only in the very frequent scenario, and in a red scenario, so in the extreme scenario, avalanche protection forest was only in a dense forest. I show you quickly how we used then these models and integrated it in interactive maps. It's a new web-based map system where we actually can interactively change forest types and disturbance types, management scenarios, future scenarios, and so show how the avalanche protection forest changes in time. So this is just the avalanche protection forest for the frequent scenario in the region of Burgund. Then we have the avalanche release areas here in blue. Then we have the velocities of the avalanches with the RAMS model in meters per second. Based on this, we could also deduce the pressures of these avalanches. Then when we do the same without forest, then we can see which forests have an effective avalanche protection forest against avalanches. So the blue ones, or the dark green areas, have an effective avalanche protection forest, which is the difference between the scenario with forest and without forest. Then on the next slide, we see which of these effective forests have a risk reduction for the buildings. These are the yellow one. Here are new wind throw areas from the Vaya storm 2018, because we wanted to know if they are in such areas with important avalanche protection forest, and where is it necessary to clean or to afforestate something. And here, usually avalanche protection forests in wind throw areas are anyway effective above 35 degrees. And here we have with red only areas above this critical threshold. So this gives us just a few impressions what we do now with these interactive maps. And I would like to conclude and give a little bit an outlook of where we stand. So reliable, automatized, and large-scale avalanche protection forest layers can be deduced from currently available spatial data. So the data are now very promising, but they have to be optimized after avalanche simulation models and after verification with regional experts. And this procedure is actually still ongoing. So we gave these maps now to the authorities, to the cantonal authorities, and then testing it in different areas. And we are communicating about that until we will have the improved and hopefully definitive version. So an update and further improvement of these maps, they are possible. For example, with higher resolution LiDAR data. Also, it's possible to have a better assessment of the terra roughness and a better assessment and differentiation of different tree species. So this will be one of our tasks in the next years. And in combination with interactive maps, this opens new possibilities for visualizing different scenarios and priority settings for avalanche protection forest management. Thank you very much for your attention.
Thank you, Mr. Baby, for your presentation. And while we wait for the questions from the chat, I wanted to ask you something. And I was wondering if these interactive maps are also meant to be published, like among public bodies or practitioners or even other stakeholders, and if and how this would influence also the output and how they look like and so on.
Yes, the idea is that we publish it, but at the moment when you go to maps WSLCA, you will not have the possibilities. And we have now also the commitment, for example, in this project with the avalanches, with the canton, that these are sensitive data and they're only for use at the moment for them. But for other data, we will publish them. And it's actually, we hope to build up a tool which is as far as possible available for other people.
Thank you. And there is a question from the chat. They want to know more about how did you define the protective forest, and what are the thresholds of an effective protective forest in your research?
Mm-hmm. Yeah, I think in order to answer this comprehensively, I need a little bit of time, and I will write it concisely in the paper for the book chapter. But it's actually dependent. So a lot depends on these tree heights, and I have different thresholds for the gaps and for the forest cover, which are dependent on the regional snow height. So this is a very important parameter, and basically also of some rules of thumbs like twice as regional snow height and so on. And we have gap sizes dependent on slope steepness. So it's quite complex. I think I cannot answer it in just 2 sentences.
Okay, no problem. Stefan?
No, we are fine. I think we are only 1 minute late, so we should move to the next speaker, but we have enough time now. So I will introduce the last speaker of this session, Dr. Christine Moos, and she's a postdoctoral researcher at the Interdisciplinary Centre for Mountain Research of the University of Lausanne, Switzerland. And during her PhD, she developed methods for risk-based quantification of the effect of forest against rockfall. And her main research actually focuses on the quantification of the effect of ecosystem-based disaster risk reduction measures. And currently, and this is interesting, or we heard this also a lot of times during this conference, she's dealing with the evolution of the protective effect of forest against rockfall in the face of climate change. And she will give us a talk entitled Cost-Benefit Analysis as a Basis for Risk-Based Rockfall Protection Forest Management. So thank you for that.
Hello and welcome to this presentation. My name is Christine Moos. I'm a postdoctoral researcher at the Interdisciplinary Centre for Mountain Research at the University of Lausanne in Switzerland. I would now like to give you some insights from our study on cost-benefit analysis as a basis of risk-based rockfall protection forest management. Rockfalls frequently endanger infrastructure and settlement, as this event on the Gotthard Highway in Switzerland in 2006 exemplifies. Forests play a crucial role in protecting against such hazards, and this at generally very low cost. A realistic valuation of this protection service is required to guarantee an efficient forest and natural hazard management. This, however, is only possible if long-term costs and benefits are considered. A risk-based approach allows for a translation of the physical effect of trees on the rockfall process into monetary terms, and thus a direct quantification of the avoided cost. The objective of our study was to quantify the protective function of forests against rockfall at local and regional scale. We present a simple method to estimate the risk reduction provided by forests at regional scale and did a profound economic valuation of a single protection forest based on a cost-benefit analysis and compared it to technical protection measures. The methodological framework was developed based on a study region along the Gotthard Highway in Switzerland. The highway is regularly endangered by rockfall, and several smaller and larger events have taken place in the past. At regional scale, we used a simple risk approach to determine rockfall risk under current forest conditions. We then used a statistical model to determine the risk reduction potential of the forest in monetary terms. This rather rough approach should serve as a basis for prioritization of regional protection forest planning. We therefore determined rockfall release areas based on a slope threshold and estimated runout zones based on the energy line principle. The occurrence frequency of the relevant block volume, here 2 cubic meters, was estimated based on inventory data. The damage potential, here the national road, was quantified based on standardized values for objects and persons. Based on this, we then calculated rockfall risk for the current forest. We then used a statistical model to estimate the risk reduction of the forest and calculated the risk without forest. The total risk along the considered road section was estimated to 330,000 Swiss francs per year. Forests in good condition, meaning a basal area of at least 30 square meters per hectare, reduce risk between 15 and 55%. Under bad forest conditions, forests can still reduce risk up to 30%. Assuming that silvicultural interventions in a protection forest are required approximately once per 20 to 30 years and that they cost about 12,500 Swiss francs per hectare and intervention, which is the maximum federal contribution for interventions in Switzerland. Protection forest management is with yearly cost of about 500 Swiss francs highly efficient in our study region. As a basis for comprehensive forest management at the local scale, we economically assess the performance of a particular protection forest complex in the study region and compared it to structural protective measures and a combined approach. We see here the protection forest complex and the flexible rockfall net currently installed above the road. We calculated the net present value of each protection measure variant for a time period of 100 years. The net present value is the sum of all future expected benefits and costs discounted to today. We considered the yearly rockfall risk reduction and revenues from wood sales as benefits and costs from timber harvest and the installation and maintenance of the rockfall nets. You see here an overview of the methodological approach applied at local scale. Rockfall runout and intensity was quantified using three-dimensional rockfall simulations. Trees were considered as single trees in the simulations and determined based on field samples. The risk reduction provided by the forest was finally quantified as the difference between rockfall risk with and without forest and considered as benefit in the economic analysis. The current forest provides a risk reduction of about 5,200 Swiss francs per year. In combination with nets, risk reduction is nearly doubled. However, only the NPV of the managed forest is positive, while the variants with nets have a distinctly negative NPV. The benefit-cost ratio of the forest is 1.7, while the other variants have a benefit-cost ratio below 1. Based on our study, we can conclude that the proposed methodology allows for a simple estimation of risk and the protection function of the forest and thus serves as an ideal basis for a rough prioritization of protection forest management at regional scale. How much a forest reduces risk finally depends on its structure and state. Thus, spatial data on forest structure are required to satisfactorily predict the risk reduction of forests. At local scale, the calculation of the NPV of a protection forest complex based on its risk reduction allows for a long-term economic valuation of the protection service and a comparison to technical measures or combined approaches. At our case study site, forest is the by far most efficient protection measure. Furthermore, the study shows that combining forests and nets can significantly increase the risk mitigation capacity of nets. With the presented methodological framework, a differentiated procedure for protection forest planning at different scales is possible. I thank you for your attention and I'm looking forward to the discussion.
So thank you, Christine, for this great and very interesting presentation. Yeah, there is currently no question yet, and therefore I would have a question to you. In your cost-benefit analysis, you have to assign monetary value to specific aspects. But what's your opinion of assigning monetary values to very difficult to quantify aspects, starting from ecosystem-based services, well-being, human life? So if you assign more positive value to a forest, probably the cost-benefit ratio then is also pretty much influenced on that. So the question is, where to stop, or is it really just scope dependent, each analysis, or what's your opinion on that?
That's a very good question, because here in this study we focus on the protection effect and revenues from forest management. And in general, I think it's very important to consider also the other values, the co-benefits, because that's something or a factor that makes the role of forests in hazard reduction even more important. But I think it is also important to look at the different factors itself and to provide a good and realistic quantification of the protection effect, and not only focus on the co-benefits. Mm-hmm. But that's something. Or finally, we should bring together all the effects and benefits of a forest. That's true. But it's very difficult to compare the different functions of a forest. That's true.
And when you talk about bringing together all the aspects, so even when you're going towards the risk assessment and even a step further, cost-benefit analysis, you are integrating lots of different calculations, modeling results, different data sets. And with each step, probably the uncertainty somehow also increases in each. So we experience this also in GreenRisk4ALPs. So we have to start to do these things, but we also realize that the uncertainties with each new combination of different data sets and models increases. So what's your opinion on that? So when should we stop? So we're talking also about now including climate change. There must some stage, there must be a balance, or I don't know.
Yeah, that's certainly true, or dealing with the uncertainties is very difficult, and the uncertainties are high. But I think that when we stay on a comparable level, meaning that we compare different scenarios, we are still more or less on the safe side, because we use the same databases for different measures. Of course, we have also different data for forests, for example, compared to technical measures, but the basis for risk calculation, for example, is the same. And when we use the results more in a comparative way, I think they are still very informative and very important. But we have to be careful with just communicating numbers, as I also showed them in my presentation. For example, this forest reduces risk by 5,000 Swiss francs per year. There we have to be careful. Yeah.
Okay, thank you very much.
Thank
Christian,
you.
do you have any more comment before I will summarize the session?
No, I think we are okay. And there are no questions from the chat, so we can go on.
Okay, so I would like to shortly summarize the session. And of course, first of all, I would like to thank all the speakers for sharing their research and for the great contributions. And actually, during the talks we got a great overview on how forests can influence different type of natural hazards and its consequences. So we saw research dealing with flooding, torrential hazards, landslides, avalanche, and rockfalls. From a more methodical viewpoint, we saw also that on how we can use remote sensing to gain spatial temporal information on the forests. From another perspective, we saw studies that focus more on the process perspective, so to better understand the processes, the physical processes behind, and the effects of forest on the natural hazard process dynamics, and also on how to improve the visualization, the maps associated to it. And finally, we also saw an approach that focuses on the quantification of consequences and cost benefits of it. So we saw a huge variety of content, and I think we are moving in the right direction. And in summary, for me, it became quite clear that the forest and its management is, or really matters when we are dealing with natural hazard and also with the associated risks. And this might be especially important, and we heard this also during the session or during the conference quite often, in the face of projected changes. So when we think on climate change, since actually we as the humans can manage and influence the forest and its structure pretty much. And finally, what came into my mind when also listening to your presentations and to your research is that probably we need also to further improve the communication and coordination between scientists, actors, and decision makers. So this seems also in this context to implement the research which we all are doing into practice. And with this, I would once more like to thank for all the contributions and for the audience for listening. And actually, I would now forward the word to Michaela Teich, which gives the closing remarks for the entire session, or conference, actually.
Thank you, Stefan. I think you also summarized the conference already very good. So like taking this interesting or new scientific knowledge and bring it into practice, and that we need to work together. And I think also networks were a great point here. So we here, this session now was so interesting for me to see what other colleagues doing, and I would like to thank them very much that they also contribute to our book, and that we learn from each other and connect with each other, and then step out of our science bubble or try to step out of it before that, to connect with the potential users of our results. And I do think that we are there on a very good stage right now, so better than, I don't know, or I think it always changes a little bit over time at the moment, also with the digitalization and people get more used to digital tools, that it might become easier, as we also saw in Emanuele's talk, that they're really like pushing to put these tools, these digital tools into practice, or the maps Peter Baby has shown. So thank you very much. And with that, I would like to close this part of the conference. We are not finished yet, but I would like to thank all the speakers and the panel members, everyone who participated here, the organizing team who put the program and the conference together. I enjoyed it very much. I hope you too, and I hope we keep talking and discussing, and in the future also hopefully in person again. So we tried our best here with this digital or virtual conference, and I think we are all looking forward to see each other in person at the next conference or meetings, workshops in the future. So thank you very much. We are now moving on to the Hofburggespräche. This will be a German part of the conference, and you're very welcome to also join us via the internet portal here and ask many more questions. So thank you very much, and hope to see you in person sometime.